Okay, so the first question I want to pose to you guys is, what is a diverging series? Has anyone ever heard of diverging? Does anyone know what it is? What is a diverging series? It's not one we use a lot, but we do or should know the difference between diverging and converging. So anyone know? You're welcome to unmute, or you can put it in the chat. No one. Yeah, like I say, it's not really one that we use a lot in terms of this types of series that we work with in geometric series, but it is useful to know the difference between the two. So hopefully I'll get some more answers for converging series. So guys, a diverging series is basically when you start to add, or when you find the sum, your sum begins to get very, very large. So a diverging series is one where the sum becomes very large. And basically what we mean there is that as we start to find the sum to infinity, so as we find the sum of more and more and more terms, what actually ends up happening is that we get closer to infinity. Now, this is actually not the one that we work with a lot, but it is important to know what a diverging series is. So a diverging series, as we start to find the sum of more and more terms, our sum just gets bigger and bigger and bigger. And so it actually just starts getting closer and closer to infinity. An example of a diverging series is the one I've put down here. So if we have a look at this example, that's right. 1 plus 2 plus 4 plus 8 plus 16 plus 32 plus 64, etc., etc., etc. So if we started to find the sum of those terms, which you can see in this block over here, as we start to find the sum of the terms, what we can see is that the sum just keeps getting bigger. So the sum of the first term, so just 1, is 1. The sum of the first two terms, so 1 plus 2 is 3. The sum of the first three terms, 1 plus 2 plus 4 is 7. And so we keep going. And hopefully what you start to see is that these numbers, these sums, just keep getting bigger and bigger and bigger. And that trend will continue as we start to add more terms. And so this is exactly what I said here. Our sum becomes very large. So that's a diverging series. It's not really one that we talk about a lot. We focus more on converging series, but there are actually two types of series when we get to geometric series, either a converging or a diverging. Like I said, this is not the one we use the most, the converging is, but it is useful to know the difference. Okay, so with that being said, does anyone know what a converging series is? And again, you're welcome to unmute, or you can pop it in the chat. What is a converging series? Mashika, you can ignore my request to unmute. You're welcome to unmute if you would like to give me an answer, but I accidentally clicked unmute on you. I do apologize. No one. Oh, grade 12, slow Wednesday. Alrighty, that's not a problem. So a converging series now is one where, nice, Kanisile, exactly. Basically, our sum starts to get very small and it doesn't go to negative infinity, but what actually happens is we call it, it tends towards a specific value. So a converging series is one where the sum, that's what we're looking at, but anyways, approaches a single value. Now that value can be anything. That value could be 1, it could be 0,3, it could be 40. But what we find is that as we start to add our terms together, they are getting closer and closer and closer to one single value. And Kanisili's comment there in the chat is also a really good way to think about what types of series are converging series. If your terms of your specific series are getting smaller and smaller and smaller and smaller as you go along, it'll be a converging series because you're adding a smaller and smaller and smaller amount each time, which means that those sums are getting closer and closer and closer to a specific value. Right, so there's a little formula that we'll deal with in a second, because like I say, converging series is the one we deal with a lot. But let's first have a look at what series could be a converging series. So if you have a look here on the left, this series that I have of a third plus a ninth plus a 27th plus 181st, plus 1 over 243 is a converging series. Back to Kanisili's point, what we can see is that these terms are getting smaller and smaller and smaller and smaller. We start off with a third. That's a decent chunk. Okay, sorry. That's a decent chunk. There's a third. Then we go down to a ninth, which will be much smaller. Then we go down to a 27th, which will be even smaller. And so we keep going, get smaller and smaller and smaller. And that is characteristic of a converging series. So if we go and have a look at the sum of the series, you can see this over on the right here. The sum of the series, if we start to add our terms up, shows exactly that. So if we just add term 1, that's a third. So that's 0,3 recurring. If we now add a third plus a ninth, that's 0,4 recurring. If we now add a third plus a ninth plus a 27, that's 0,481, 481, etc., etc. Excuse me. And as we start to add our terms, we're getting closer and closer and closer to a specific value. And in this case, our series is converging on the value a half. So as you can see, these values are getting closer and closer to 0,5. And so we say it converges, it approaches a single value of a half. Now, like I said, converging series is the one we're going to work with all the time. I've personally never seen a diverging series question because it's not, there's nothing special about it. That's quite mean, but it's just, it doesn't show this unique relationship of, even though we're adding an infinite number of terms, we only ever approach a single value. And so the converging series is a really important sort of takeaway from this lesson. That's what we're going to focus on. Now, another really important thing to know is that a series will only converge when R is a fraction, basically. It could be a negative fraction, it could be a positive fraction, but essentially when R is a fraction. So I'm just going to write under here, when R is a fraction. So as long as R falls between -1 and +1, you will have a converging series. This makes sense, right? If your R value is a fraction, you're getting smaller and smaller and smaller. Whereas if we go back and look at this diverging series, our R value is 2. I'm multiplying by 2 each time, getting bigger and bigger and bigger. It can't converge. It keeps getting bigger. So this point of the range of R is also really important. And that range, I would really encourage you to remember, because we often ask questions that rely on you remembering that the R value must fall between those two numbers. And we're going to do some questions like that a bit later. So converging series is when it approaches a single value despite adding an infinite number of terms. And really importantly, it is when R is between -1 and +1, not including those values, but greater than or less than -1, +1. Okay, so we've learned about quite a few formulas when it comes to geometric series. We've learned about the TN formula. We learned on Monday about the sum formula. And whilst this is a sum to infinity, we actually have a special formula for sum to infinity. It's a much shorter formula. We don't have to remember, well, it's just a slightly shorter formula, not as many terms to work with in my fraction. But our sum to infinity formula for a converging series is rather S of n, so the sum of n terms, over, sorry guys, 1 minus r. Don't know why I'm writing it down, because it is actually right there. So that was an irrelevant thing that I just did. That is our sum formula. The sum to infinity of a converging series is equal to a over 1 minus r. And really, really, really importantly, this only happens when r is between -1 and 1. If r is not between or in that range, it is not a converging series. All right, so there'll be questions where we say, is this a converging series? And then if you show that r is in that range, yes, it's a converging series. There will be questions where we have variables, like I've always said. Often we introduce variables into our questions. And we will say this is a converging series, or for what values of x will this series converge? And knowing that range for r is going to help us. Okay, so I'm just going to do that in case anyone wants to take a screenshot of that information. But we're going to have a look at an example now of how we use the sum formula, or the sum to infinity formula. And then obviously we're going to increase in complexity in our questions as we go along. And remember, guys, please jump in if you have any questions or anything you want to know. You're welcome to unmute yourself, but you are also welcome to put it in the chat. I've got it open. I will see your questions or your comments. Alrighty, so let's have a look at an example. If I look at my first example, oops, I am saying calculate the sum to infinity of this geometric series. Sorry. So we've got this geometric series over here, a half, a quarter, an eighth, etc., etc., etc. Now, automatically, we should be thinking, my terms are getting smaller and smaller and smaller, so it should be a converging series. But obviously, for us to be certain of that, we can double check. So, oops, we know our a value is a half. And if we go and find out what our r value is, we will know whether or not it's converging. So r would be a quarter divided by a half, because remember your r value is found by taking term 2 and dividing that by term 1 or term 3 over term 2, or whatever, as long as you're dividing consecutive terms. And we get our r value. So r in this case is a half. Now, if you go back to what we said, r has to be between -1 and 1 for it to converge. In this case, it does. And so this is a converging series. Because it's a converging series, I can use my sum to infinity formula, which is nice and easy, a over 1 minus r. So my a value, as I've already said, is a half. 1 minus my r value, which is a half. And guys, whilst you don't have to, whenever I substitute in, I use brackets, because if this had been a negative a half, what we would end up with in our denominator would be 1 minus negative a half. And so we would need to remember about that sign change. When we've got those two negatives, it becomes positive. So we just need to be careful when we are substituting. Obviously, how you choose to do it is up to you, but just bear it in mind. I choose to use brackets when I substitute. I find it easier to see when there's a sign change. Right, then all you do is put that in on your calculator. So a half divided by 1 minus a half, which is equal to 1. So in this case, what that's telling us is that if we add all of these terms up all the way to infinity, that sum is going to approach or converge on the value 1. So it's just going to get closer and closer and closer and closer to the value 1 as we go along. And that really is how we use the sum to infinity formula. Know what a is, you know what r is. Double check that r does fall in the range that we want. So this -1 to +1. And then sub it in your formula and Bob's your uncle. All right, so let's take a quick screenshot of that. And then in case you can't see, we're gonna try by ourselves. Same as always, we are, or I am giving you two options, a slightly easy one and a slightly harder one, or I mean, I say harder, a little bit more complex. You decide which one you would like to do. So decide sort of how you feel about being able to use the sum formula. If you're not feeling too confident, pick the easy one. If you are, pick the slightly harder one. And then we'll go from there. I don't think you'll need a lot of time for these questions. I'm going to give you about 2 minutes, and then we'll check the answers. All right, but here are your two questions. So the slightly easier one is, the series 2 2/3 2/9. The slightly harder one is -64, +32, -16, and so we keep going. So remember, first double check what R is. Make sure it does actually converge, so make sure it's between -1 and 1, and then you can go and find the sum to infinity. Right, I'm going to unmute myself so that I don't feel the urge to speak. But 2 minutes, obviously, if you've got questions, unmute yourself, put it in the chat, put your answers in the chat as you go along. It might help someone else, and then we'll have a look in 2 minutes. If when you're done, guys, if you don't mind just giving me a thumbs up, just so that I know you're done. Nice, guys. Keep those answers coming. Nice, grade 12s. Okay, looks like most of us are done. Awesome. Okay, let's have a look. So I'm seeing some nice answers, which is great. Just double check as we go along, obviously. So if we have a look at the slightly easier one, remember, first work out what R is to double check that it does converge. Sometimes we do say to you, given the converging geometric series, and then you don't have to stress, you can assume it does converge. But when working out R, as long as it falls in that range, you're good. So in this case, R was 3, which obviously does not fall in that range. So clearly my brain has just lost the plot entirely, unless I can't do maths. It's not 3, guys. It's a third, because you know. Right, I'm correcting myself. I do apologize. Okay, there we go. So R is a third, falls within the range, so we're good. So when we now go and substitute that into our formula, we get that the sum to infinity is equal to 3. My apologies, grade 12s. My brain is a little bit mushy. All these bugs flying around, and clearly it's now affecting my brain. Apologize. Okay, so sum to infinity is indeed 3. Our R value fell within the range of -1 to 1, and so we're sorted. Okay, I will make it a bit smaller for you to screenshot. Let's hope I can do this one properly. If we now take the slightly harder one, now guys, this is only slightly harder because of the negative, positive, negative, positive. And I explained this on Monday, that this often happens when well, it always happens when our R value is negative, because what you're doing is you're timesing term 1 by a negative, so it becomes positive. That positive term by negative, so the next one's negative, and so it keeps alternating signs, and that's how we know R is negative. So in this case, R is equal to -1/2. When we substitute that into our sum to infinity, we get -128/3. Now, we did discuss this on Monday about whether or not you should round off or not. Obviously, remember grade 12s, the second you start rounding off an answer, you are essentially making it inaccurate. It's no longer the accurate form of its value. So I would advise trying to leave it as a fraction. It's not the end of the world if you write it as a decimal. We're not going to, mark you wrong, but my advice is leave it as a fraction, because this is the most accurate form of the answer. You're not rounding off anything, so you're not starting to estimate values. I would leave it. If you didn't, your answer was -42,67 if you rounded off to 2 decimal places. So it was 6 recurring. If you wrote it as -42,6 recurring, that would be fine as well. My advice, just leave it as a fraction. I personally don't enjoy decimals. I have a thing against them for whatever reason. Just don't do it. But if you do, remember to round off correctly. But where possible, just leave it as a fraction. It's way more accurate in terms of what you're trying to express the value is. Alrighty, so there are the two. Let's take screenshots of those, and then we're gonna step it up a little bit. All right, so the next question, sorry, is looking at recurring decimals. Now I'm going to scroll back up to the top in a second, but in grade 10, literally like one of the first things we teach you in algebra is how to convert a recurring decimal to a common fraction. And there's a whole like equation you have to set up. You multiply it by the factor of 10 that you are like the number of values that are recurring. You subtract equations. Now that's all well and good, but if we go have a look at this converging series that I gave you right at the start, what I want you to see, or what I want you to notice, is the fact that these sums that I'm getting here all have recurring decimals in them. So it's 0.333, 0.444, etc., etc. They are recurring decimals. And so what actually happens is when we find the sum of, or sum to infinity, what we get is a recurring decimal. We've just seen this in this question that you had here in the medium question. It was -42,6 recurring. And so what that means is that we can actually use our sum to infinity formula in order to convert recurring decimals to common fractions. Now, I'm not going to spend a lot of time on this because we'll ask you maybe a question on this. It's not a huge thing that you need to stress about, but it is really cool. And it is quite helpful to be able to convert the two. So if we have a look at our first one here, we want to convert 0,3 recurring to a common fraction. Now we all know what that is as a fraction. That's a third. So we sort of already know what our answer should be, but obviously we need to show all of our working out. So the first thing you need to ask yourself is how many numbers after the decimal are recurring. So that's the first thing we need to figure out. And maybe I should be clearer, how many different numbers recur or repeat. And in this case, it's only one. So if we wrote this out as a recurring decimal, this is sort of the situation we would have 0,33333, etc., etc. So in this case, I actually only have one number that's repeating. It's 3. What we now want to do as our second step, or as sort of the next part of this process, is we now want to write our recurring decimal as a series. Now, it does go back to what you learned in grade 10 in terms of how to do this, in that we are going to use factors of 10 in order to write it as a series. I do apologize. So essentially what we want to do is, this would be term 1, term 2, term 3, term 4, etc., etc. But we need to remember that this is the first decimal place, the second, the third, the fourth, and so on. Now, every time you move the decimal, it's a factor of 10. So that's something we need to remember. And again, something we built this foundation on in grade 10. So to write this, if we just look at the first term, that is a tenth. It is one placeholder or one unit after our decimal. So this first term would be 3/10. It is 3/10. First placeholder after the comma, 3/10. If we now have a look at the second term, this is now in the 100th placeholder. So this next term of the series would be 3/100. If I move on to the next one, this is now in the 1000th position. So plus 3/1000. I'm not going to keep going because we don't need more than 3 terms. But essentially, this is what we're doing. We are creating a series from our recurring decimal, bearing in mind where its placeholder is. Is it in the tenths, the hundredths, the thousands, the 100,000s, etc., etc., etc. But what I have now is a geometric series. It's getting increasingly smaller, so it will have a sum to infinity. Hence, we can write it as a common fraction. And now, essentially, we can do exactly the same thing. So we want to work out our A value, which we know it's 3/10. We need to work out our R value. So remember, it'd be term 2 divided by term 1. And that would give me an R value of 1/10, which kind of makes sense. The number only repeats, or there's only one repeating number. So 1/10 sort of fits in with that. And now we can work out our sum to infinity. So A, 3/10 over 1 minus R, so 1 minus 1/10. And remember, grade 12, you just put this in on your calculator. You don't need to try and do tip and times and LCDs and all of that stuff. Just put it in on your calculator. So our sum to infinity here is, what do you know? 1/3. And remember, we said right at the start of this question, we already know that this fraction should be 1/3. It's one of those like recurring decimals that we just know the fraction of. And so through using series, we're able to actually prove that the common fraction is indeed 1/3. So this is a really cool way to look at recurring decimals as actually a pattern, and then use the knowledge we have of sequences and series in order to convert. There's obviously nothing wrong with using the method you learned in grade 10 in terms of, like I say, setting up those equations and subtracting them. But we have this knowledge now. We have a formula that we can use. Why not use it? Alrighty, I will make this small in a second, but let's have a look at a slightly different example where now we've got 0,16 recurring. Now, just so that we're all clear, because I don't think it's common knowledge, this line on top of the 1 and the 6 also means recurring. So we could have represented this as 0.16 with dots on the 1 and the 6 to show that they recur, but the line also shows that. So depending on the numbers that the line covers, those values recur in the decimal or in the number that we're working with. So I'm more just showing you that so that if you see it, you don't panic, but it does mean recurring. Okay, so step 1, we go back to our steps here, is how many different numbers are recurring. So if we go and write this out as a recurring decimal, we now need to be mindful of the fact that it's actually 2 values. It's 0.16, 16, 16, and so on. So there are 2 numbers that are recurring now. So now I need to be careful because I don't really want to split up my recurring numbers. I kind of want to keep the 16s as a group. We want to keep them as a pair because otherwise the recurring sort of ness of this pattern is lost. Because 1 and 6 separately is just 1 and 6, but the pattern is 1, 6, 1, 6, 1, 6, 1, 6. So we want to keep them as a pair. So that was the first step. The second step was write it as a geometric series. Okay, so in order for us to do that, we now just need to be a bit careful because now we've got 2 numbers recurring. In the first sort of grouping, this is the tenths and the hundredths. I go always to, I don't know how to say this in like proper English, but we sort of go to the biggest decimal that we're working with. So in this case, it's tenths and hundredths. So the biggest one is hundredths. So I would say 16 over 100, mostly because I'm lazy to pull up the calculator. If I take 16 over 100, they are my first 2 decimal points, 0.16. Okay, so that is giving me the first 2 decimal points after my comma of my recurring sequence. If I now go to the next one, so this was the tenths and the hundreds, we've now got the thousands and the 10,000s. So I would have 16 over 10,000. If I put that on my calculator for you, just so that you can see. Obviously now it's going to be in scientific notation, which is not really what I want. Ay, ay, ay. Calculators. Okay, let's try this again. Maybe it'll work, maybe it won't. There we go. No, didn't work. Right, if you put it on a calculator and you converted it from scientific notation, this would give you 0.0016. It gives us that second group of the 16 recurring. And so we keep going. So that was tens, hundreds, thousands, 10,000s, 100,000s, millions. So this last group is the 100,000s and the millions. So we would have plus 16 over 1 million. Again, I don't need any more than 3 terms. Actually, I don't need any more than 2 terms. But the point I'm making is now it's every 2. So we just need to bear that in mind for our denominator. Once we've done that, we have a sequence. We can now use our formula. A is equal to 16 over 100. Now, grade 12s, obviously that can be simplified. But for sake of not confusing the situation and your calculator is going to simplify the answer anyways, just leave it. Right, we do need our R value, so that would be the 16 over 10,000 divided by 16 over 100, and so that gives me an R value of 100th. Again, makes sense. I'm now repeating every hundredths, essentially, because of those 2 decimal values recurring. So now I can work out my sum to infinity, A over 1 minus R, so 16 over 100 divided by 1 minus that 100th. And like I say, your calculator is going to simplify it, so don't stress. Chuck that into your calculator and you get 16 over 99. Okay, so now if I put that in on my calculator, remember our recurring decimal is 0.16. Put it in scientific notation. Oi, oi, oi. There we go. 16 over 99, and there is the recurring decimal, 0.1616161616, etc., etc. Okay, so this is just a really cool way to think about series. It's a really cool way to convert our recurring decimals, should you need to. Like I said, we would maybe ask you a question. We are not going to ask you more than that. There's no point to it. There's other nice questions that we can ask you, but it is a nice question in that you see the pattern in the recurring decimals and you can apply knowledge that you have in order to work out what the common fraction is. All right, so let's take a screenshot of that and then you're going to try by yourself. Again, pick the one that works for you. If you feel more comfortable with a slightly easier question, do it. With a slightly harder question, do it. Do both, whatever your heart desires. But you're going to give those a try now. I'm just going to wait for screenshots and then I'm going to move. And remember, please ask questions if you need. Okay, so here are your two options. That's a weird looking recurring over here, but basically it's 0.25 recurring, where the 2 and the 5 is recurring. Sorry, the dots are a bit odd. Either you're going to convert 0.1 recurring or you're going to convert 0.25 recurring. I'll give you like 5 minutes and then we'll have a look at the answers. Again, I'm going to mute myself, otherwise I feel like I have to talk. Remember, feel free to ask questions if you need. You can just unmute yourself or you can put it in the chat. And guys, remember, because you're getting a fraction, type it into your calculator and make sure you do actually get the recurring decimal that I gave you initially. Liking the answers I'm seeing so far, grade 12. Really, really nice. Well done. Okay, can you just give me a thumbs up if you're done? So that is 5 minutes, but if we need a bit more time, I'm happy to give you another minute or two. Nice answers, guys. Okay, it seems like most people have answered or given me a thumbs up, so let's have a look. Okay, so for the first one, it was 0.1. So what we needed to realize there is that it's only one decimal or one number being repeated. And so we just go up in tens. So tenths, hundredths, thousands, etc., etc. Our R value then was a tenth. And so when we substitute into our formula, we get 1/9. And again, you're told put it into your calculator. Make sure you do get 0.1111 recurring. For the slightly harder one, it was now two values that were recurring after a decimal. And so now we had to go up in hundreds. So hundreds, 10,000s, millions. Your R value though was 100ths or 1/100th. And so again, put it into a formula and you get 25/99. If you put it into a calculator, you do get 0.25252525. So what's quite nice with these is that you can check yourself. Put it into the calculator, make sure you do get the recurring decimal that you were given, and then at least you know you're on the right track. All right, but like I said, don't stress too much about these types of questions. It is nice to know, and like I say, you'll probably be asked one, but no more than that. But it is an application of sequences and series, and application questions, like I say, you will be asked. All right, I'm just going to wait in case anyone still needs to take a screenshot. Otherwise, we're now going to have a look at an example with variables. And like I was saying at the beginning of the lesson, actually using the knowledge that a converging series is where R is between -1 and 1. Often we panic with these questions because of the variables, but they're not hard questions. They're actually very doable. We just have to read carefully and just know what it is that we're working with. Okay, so looking at example 3, we have been told that we have, okay, I should say a geometric series, but let's just assume it says geometric series, p plus p times p plus 1 plus p times p plus 1 squared, etc., etc. So hopefully what you can see is that each time in my pattern, the exponent is going to increase. So the next one would be p plus p times p plus 1 cubed, and so we would keep going. So it's the bracket that I'm actually sort of using as my ratio each time. You'll see this now in a second. So question A says, for what values of p will the series converge? Now remember, a converging series is where R is between -1 and 1. And so that is the knowledge we now need to use when we answer this question. First thing though, I need to work out what my R value is. To work out my R value, remember it's term 2 divided by term 1. And in this case, term 2 is that p times p plus 1 divided by term 1, which was just p. What we can see now, grade 12s, is that the p's divide away because p divided by p is 1. So those essentially go. And so all we're left with as our R value is that bracket. And that's exactly what I said earlier. We can see that the bracket is the thing that's being affected as we go from term to term. So that's going to play a role in my R. Now that we know what R is, all we need to do is substitute it into that range. That is it. Okay, it's asking for what values of P. So there'll be a range because that values gives me a hint. I know what R is. Yes, it's in terms of P, but that's fine. I'm just going to solve an inequality in terms of P. So -1, put in my R value, P plus 1, is less than 1. That's all I'm doing. I found R and now I substitute it into that range because I know that that is where the series will converge. Now this should take you back to your grade 10 inequalities. So remember, when you've got your variable sitting in the middle here, when we start to solve this equation, if we're going to say, for example, here, subtract 1 in the middle, we would need to subtract 1 on both sides of this inequality. You can't just do it on the right. You can't just do it on the left. You need to do it on both sides. So this is going to give me -2, p in the middle, 0. Okay, because inverse operations, I'm going to essentially solve. And so what this is telling me is that as long as p is greater than -2 but less than 0, I will have a converging series. All right, so sometimes just ask, sorry ma'am, isn't p times p plus 1 one term? Yes, so here's your first term, here's your second term, here's your third term, and so on. So when we now go and work out our R value, T2 is the p times p plus 1, so that one whole term. But then we divide it by term 1, which is p. And so the p's end up dividing away. I hope that answers your question. But yes, p times p plus 1 is one term. And that's why I put that whole p times p plus 1 in my numerator. Cool, no problem, Simtanda. All right, guys, so now we know where it converges. So as long as p falls in that range, we're good. No issues. So the next question says, assuming the series is convergent, calculate the sum to infinity. Now we just need to be careful. We've discovered, or we have found out what range of values p can be, but the question hasn't said, assuming p is -1. So we still don't actually know the exact value of p. So how are we going to calculate the sum to infinity? Well, we know our formula is the sum to infinity is equal to a over 1 minus r. So let's substitute in what we know. We might actually see that it simplifies and terms cancel out. Can you see, Leah? Please repeat the last part of the other question. I'm not too sure which last part, so I will just wrap up what we did and hopefully that'll help. So guys, I'm just going to quickly wrap up what we did in question A. So we want to know for what series of p the series converges, and we know that the series will converge when r is between -1 and 1. So what I do is I take term 2 and divide it by term 1. You can see they're highlighted there. So term 2 is p times p plus 1 divided by term 1, which is just p. And what we saw is that the p's divide away. So p divided by p is 1. They're gone. And so that leaves me with an r value of just p plus 1. Now that I know that, I can substitute it in place of r. And so I've got -1 is less than p plus 1, which is less than 1. I quite literally take the r value that I've just worked out, p plus 1, and I put it in the middle of that inequality. And then I solve the inequality. So I would have to subtract that 1 because I don't want the plus 1 in the middle. I just want p left in the middle. But I would need to subtract 1 on both sides of the inequality. And so -1 minus 1 is -2. 1 minus 1 is 0. And so now I get this range of my p values. Can you see there? I hope that helps. Just let me know if there's something that I said earlier that I didn't, but I hope that helps. Just like I said, shout if not. So if we have a look at question B, guys, so assuming the series is convergent, calculate the sum to infinity. Cool, well done. We don't know what p is, so we're not going to guess. We can't just make a guess, but let's substitute in what we know. So we know a is p, and we know r is that p plus 1. Now this goes back to what I said earlier. When you substitute, use brackets, because r is a multi-termed expression. That's a binomial. So I would actually need to distribute that negative, remember that's a -1, into that bracket. And so what I end up with is p over 1 minus p minus 1. And hopefully what we see here is that 1 minus 1 is actually 0. And so what I'm getting is that my sum to infinity is p over -p. And then back to just the basics of algebra, p divided by -p is -1. And so my sum to infinity here is -1. The series converges on the value -1. Okay, so even though we weren't told what P is, we were told that it is a convergent series. So use the formula that you have, sub in what you know, even if it's in terms of P or X or whatever, sub it in, because you will hopefully be able to do exactly what we've done here and cancel out variables and terms and essentially land up with your sum to infinity. Okay, so we often stress about these questions because of the variable. 9 times out of 10, variables just stress us out when we feel like they shouldn't be there. But read your question carefully. As long as you know what converging means, you can apply that knowledge, that negative R is greater than -1, less than 1. Having that knowledge, and it's the same as all the other sequences and series that we've done, knowing that a quadratic is a second difference, knowing that arithmetic is a constant first difference, knowing that geometric is a constant ratio. Having all of that knowledge allows us to solve for unknowns. We use all of that whenever we solve for an unknown, and there's no difference here. Knowing what a converging series is allows us to solve for our p-values. All right, but